The task is not to see what has never been seen before, but to think what has never been thought before about what you see every day. Erwin Schrödinger. In an early attempt to construct a story that accounts for reality's persistent physical properties, Plato advanced the idea that the elemental building blocks of geometry are also the elemental building blocks of reality. That is, Plato proposed that the 5 simple shapes that are constructible from faces whose sides are of equal length, the Platonic Solids, are atoms of fire, air, earth, water, and ether. If geometry is fundamentally responsible for the constructs of physical reality, then humanity has a path towards implicitly obtaining the logic of existence. With the light of Plato's candle, it becomes possible to walk ourselves out of the cave of ignorance. For eons, answering the call of existence and making one's best attempt to make sense of things meant studying the Platonic Solids. If you wanted to better understand reality, you would spend your hours staring at these shapes, trying to divine anything else these elemental constructs might have to say, trying to figure out how they combine to build the world we see. And yet, despite all the people examining these ideal mathematical objects for further clues, despite the specific effort to understand them as well as possible, a basic connection between these geometric shapes went unnoticed for 2,000 years. When Leonhard Euler looked at the Platonic solids, he noticed that they are connected by a single elementary geometric relationship. Every one of them maintains the same balance of 0, 1, and 2-dimensional features, vertices, edges, and faces. That is, each shape's number of vertices minus its number of edges plus its number of faces is always equal to 2. However obvious and simple this fact may now appear once it's pointed out, the question we must address is, how did everyone else miss it? Despite the intense interest in these objects and the generations of people searching them for clues, nobody had ever found what Euler found. Why? It doesn't take much time to count up these properties and compare them, yet nobody had. Why not? The answer is that before Euler, nobody had imagined that an object's number of sides was a feature worthy of attention. They had never seen anyone else care about such a feature, so it just hadn't occurred. Euler was the first to count up these features and compare them because he was the first to imagine the option, the first to see them as features. Conscious thinkers have only 2 routes to new thought, through example or through genuine new reaches of imagination. Just as it is usually easier to verify an answer than to find one, it is usually easier to follow a line of logic laid out for you than to lay one out for yourself, which is why conscious thinkers almost always follow. The trouble is that if we are always just following, then we can get seriously stuck. If nobody has ever shown us an example of being interested in the number of edges an object has, we can all stare at something for 2,000 years without seeing what's right in front of our eyes. Euler looked with new eyes, under his own investigation, instead of looking as he had been directed to. And in that moment, the world inherited new conceptual powers. Another famous example of how difficult it can be to take the next logical step without anyone showing us how comes from our history of conceptualizing gravity. For millennia, humans personally pondered why things fall to the ground. But it wasn't until Galileo came along that anyone thought to measure how things fall under the influence of gravity. Galileo's measurements could be performed by nearly any human within minutes, with no cost, like rolling a ball down an inclined plane and marking the position of the ball down the ramp at successive increments of time and then comparing the distance between those marks. But before Galileo, nobody had tried. Nobody had thought to. By extending the powers of measurement to gravity, Galileo became the first to see it more clearly. And what he found is that gravity's action depends on an inverse square law, In other words, he discovered that gravity is geometric. This fact about gravity had always been true. It had always been staring us in the face, screaming from every freefall occurrence ever witnessed. But nobody had seen it before, because nobody had thought of gravity as a thing to physically measure, a thing to look into that way. Through his efforts, Galileo came to one of the greatest insights of all time, that the truth about reality is right in front of our eyes. The task is simply to see more clearly, to more explicitly conceive existence. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. Galileo Galilei. Today's best geometric description of the fundamental structure of reality is called quantum field theory. This construction naturally produces all of the actions of quantum mechanics and special relativity, a feat that earns it the title of being the pinnacle achievement of science. The problem is that although this construction makes the right predictions, nobody understands why it has that particular construction. The parameters of quantum field theory have no story themselves. Every single one of them remains utterly unexplained, known from experimental measurement only. That is, we cannot explain why quantum field theory is constructed as it is. We cannot predict its parameters to any degree of accuracy at all. But once we construct our field theory with those parameters, the actions of quantum mechanics and special relativity are reproduced in full. Today, any serious investigation of reality involves staring at the parameters of quantum field theory, in search of the logic connecting them. That is, the modern version of the quest to tell the accurate story of reality's construction, now called the theory of everything, quite literally boils down to explaining the parameters of quantum field theory, explaining why they are what they are. Don't let the numbers be intimidating. I'll help you guide through what you're supposed to be paying attention to. All right, so here's the list of the parameters of quantum field theory. I've broken it into two groups. First, just the masses of the fundamental particles of matter. There's 17, okay? You probably recognize most of these names already. The electron, proton, neutron, charm, quark, down quark, up quark, strange quark, beauty or bottom quark, truth or top quark, Higgs, Z, W bosons, tau, muon, the tau neutrino, muon neutrino, and electron neutrino. Okay, that's it. Those are the fundamental partitions of mass, the slice sizes of mass that exist naturally in nature. Why? Well, we'll get there actually in this book, but there has, up until now, been no proposed story. So that's what we want to be very, very clear on. In this puzzle, we have these pieces, we have these values of measurement. I guess the last three you can see, the neutrinos, we only know that they're greater than 0. There's some value there, but it hasn't been specifically individually measured. Since these are measures of mass, they're in units of kilograms. And you can see that they're all in scientific notation here, where they have powers. So 10 to the negative 31 kilograms is the scaling that's associated with the electron, right? And then it has a very specific string of digits. You can see how many we've measured. Let's just point out the things to notice here. If you were to give me a position to meet you with 3 significant digits of accuracy, or 4 or 5, imagine how accurate it would be, right? You tell me within 0.1 meters how close you want me to be to find you, or 0.01 meters, or 0.001 meters. You're getting really, 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 really accurate fast. These numbers, like the mass of the electron here, the mass of the neutron and proton, they represent the numbers with the highest measured accuracy in all of science. Okay? The electron, proton, and neutron are things we know as well as anything in all of science. And you can see where our error bars are. Okay, all the way out there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant digits, but in the 10 and 11th digit, it's plus or minus 28 is the error bar. Okay, so this is how we're reading it. The parentheses refer to the 2 digits preceding, plus or minus those, okay, by that amount. Okay, now let's move on to the second half of constants that you would have to make sense of in order to give the story that generates quantum field theory, that makes sense of its stretching parameters, okay, that makes sense of its construction. You probably recognize several of these, but I doubt anyone recognizes all of them unless you're already really been studying this, right? Fine structure constant, world famous, super famous in physics. Dirac, of course, basically said that until you make some sense of the fine structure constant, you've done nothing that we really need. This is the gateway to understanding the rest of reality. The electron's charge, there's a constant. The Compton wavelength, the Josephson constant, Planck's constant, electric constant. We go all the way down the list. What I want you to pay attention to right now is just that we have a symbol for each of these parameters. For each of the puzzle pieces in quantum field theory has a symbol, right? We have 17 masses. And then now we go down this list of constants, and each one has a symbol, but each one's represented by a number. And look how well we know each number. Again, these are the numbers we know best in science, okay? So accounting for these numbers doesn't just do a good job, it literally accounts for the highest standards done in science today. Literally. If you could count for any one of these numbers, all the way out to all of its significant digits, that would be doing the highest, well, we just streamlined past that. No one has accounted for any of these numbers, ever. No one's ever proposed a story that's predicted the fine structure constant. No one's ever proposed a story that's predicted the value of the electron charge. None of the values of the parameters in quantum field theory have ever been predicted with any accuracy at all. Let's say you just need the first 4 significant digits for the mass of the electron. No one's even done that. No story at all has gotten us any closer to understanding these values. They have remained complete unknowns. As far as I'm aware, no one in the world's studying this besides me, which is why I wrote this book on it. It's something that everyone should spend time on, of course. These are the central parameters that code our geometric understanding of reality. Literally, to the error bars. This literally lists the most important constructive parameters of existence right here, and it's never really a conversation for some reason. In fact, when you do watch or pay attention to the conversation that's going on about physics, they always avoid these by just putting everything down to natural units of 1, so that you don't even see what these numbers are. All right, so I think it's really important to take a little bit of time to look at them, but you don't need to memorize any of the sequences. It wouldn't do you any good as far as I'm concerned. What you need to memorize is, or get familiar with, is that these numbers are known so well, okay? They're extremely accurate. And notice that each number is either dimensionless. We can start again at the fine structure constant. It's dimensionless. It has no measure attached to it. It doesn't express itself in time or space or charge or mass or temperature. It's a self-referential geometric measure alone, like pi, okay? So, fantastic, beautiful number. But it means it also needs to be understood geometrically. For us to ever say that we understand the fine structure constant, that would mean we need to understand what geometry it refers to, the same way we understand what pi refers to, circles and spheres and so on, right? That's the goal. Most of them have units attached, and several of the units, but all of the units involved here, we're talking about just measures of time, space, charge, mass, and temperature. Or you could there's a couple of here with mole. I think that's not a measure of dimension, it's a measure of amount. Okay. All right, so everything's broken down into measures of the 5 fundamental dimensions of physical reality. And not just in any scaling, but in the one coherent system of units scaling that science has figured out you have to use, right? That people think that meters is random and seconds is random, but in the system of units we use in science, you could only claim maximum up to one of them being random, because once you have meters, we've connected our description of time to it. right? There's no more randomness individually between them and the rest of the measures. So this coherent system of units is the unit system used in science for lots of reasons, but most importantly, the coherentness of it, meaning if you have a description of one dynamic, you can transfer from that dynamic description to another dynamic description, a whole different equation, without having to do any skewing weird factors, so long as you always stick to this one coherent system of units. Okay, so if you're not familiar with meters and seconds and Kelvin and kilograms and so on, they're scary. You just need to know that they're representing 5 different independent dimensions or measures. Okay, they're unique measures. That's good enough for now to hold on to. All right, so we have this list. We're now keeping track of the parameters of quantum field theory. We also now very explicitly have a laid out target, right? This is our goal. If you can explain all of these numbers, then you've completed a theory of everything. You've literally if you could geometrically relate all of these and predict all of these, you would then have found the geometric goal, right? The theory of everything. To do that, we need to investigate these numbers very meticulously. So now let me continue on with the reading of the book. This book tells the story of these numbers, revealing that the combinatorial logic behind the structure of reality is mapped by the minimal self-balanced manifold, the hyperbolic figure-8 knot. That is, in this book we notice for the first time that the ideal minimum geometry, the one that defines the minimal possible persistent stage, is the stage of physical reality. A little sidebar here, let me be very clear. I am saying that by defining explicitly the partition balance of the 5 actions that compose together to make the hyperbolic figure-8 knot balance, we define and predict boundary conditions. You get 5 unique boundary conditions from that, which actually define the Planck constants, the mysterious cutoffs in time, space, charge, mass, and temperature in our physical reality that have not been explained. These numbers are actually predicted by the partition balance or the boundary conditions of the partitioned actions that make up the hyperbolic figure-8 knot. Okay? It's a really big deal. But then we went even further in the same paragraph to point out that, hey, once we have these boundary conditions, when we look to see at the balance of boundaries that are being maintained in this balance and label all of those, geometrically define them, they predict all of the constants of nature, including the mass assignments of the fundamental particles of matter. No story has ever predicted any of these, remember? And we now have one simple geometry that's predicting them all, and not just a simple geometry, the one that's defined mathematically as the simplest self-balance geometrically possible. I hope these extra commentaries are helping, but I'm giving this a try for the first time, so give me feedback and let me know what is helping, what's not helping, and also what questions do you have so I can just continue to add the discussion. All right, in summary, in this book, we discover that the set of fundamental structural traits of physical reality, the elemental partitions of charge and mass and the constants of nature, are the set of unique geometric properties that define the simplest manifold balance, the hyperbolic figure-8 knot. So this book will be an expose of the hyperbolic figure-8 knot. It is not a new concept or a new geometry. It's well known as of the 70s. And let's get into that. Chapter 0, the simplest manifold balance. In the mid-1970s, Robert Riley and Troels Jorgensen independently discovered that the figure-8 knot emits a complement with a hyperbolic structure. This is the first known example of a hyperbolic knot, a closed loop under hyperbolic balance. Now, it's worthwhile, a little sidebar again, it's worthwhile to spend some time trying to get an intuitive understanding of this geometry. So let's take a quick look here at this shape, the complement of the figure-8 knot. First thing to notice, if it's your first introduction, is the cutouts are not part of the shape, but that's just so we can see inside. Fill in the cutouts symmetrically, and that's the shape we're talking about. Notice that shape divides back up. How should you imagine the shape? What are you looking at when you look at the shape? Well, first of all, imagine that you've got wave action suspended in 3D. You've got waves coming together, intersecting. Imagine that the wave twisted the fluid like this, but that this shape we're seeing is the boundary that divides the action that the fluid's being balanced under. Meaning, once you've made this balance, you've divided the fluid into internal and external actions, domains. Look inside the shape, there's a torus region that goes around the figure eight in the middle. If you're some fluid that's in that region, you will never escape to the outside, right? You'll twist around inside that torus region, go all over inside there, but you're never going to go outside the white boundary. If you're outside, you'll never go inside the white boundary. Now you can go in the funnel, right, and zip down through the inside, twist around, come back out, but you will not make it into the toroidal region inside. So, first thing to notice, if you've got a wave action that balances into this division, into this geometry, then you've got a system that's permanently balanced into an internal region and an external region, okay? The external is all outside of this. We're only seeing the division between the two boundaries right now, but that's where we're starting. The hyperbolic figure eight knot is a double cover of the Gleisking's manifold, the simplest among all the non-compact hyperbolic manifolds. As such, it defines the minimally self-balanced state. In other words, persistence is minimally obtained when a filament, a finite wave element, becomes balanced under local cyclic action, twisting and folding into the shape of the hyperbolic figure eight knot. The internal volume complement of this minimal geometry is equal to twice Gleisking's constant. This is a number like pi. It's a constant of geometry, okay? Intrigued by this ideal geometry, William Thurston, who you may have heard of, looked closer and discovered that the complement of the figure eight knot decomposes into a union of two regular ideal hyperbolic tetrahedra. He then formulated his geometrization conjecture, claiming that all three manifolds admit a certain kind of geometric decomposition involving 8 geometries, most of which are hyperbolic. And Gregory Perelman proved this conjecture in 2002-2003. Thurston's decomposition was a brilliant addition to our knowledge of the hyperbolic figure eight knots geometry, but it didn't tell us everything there is to know. That is, it wasn't explicit enough to define every feature of this minimal geometric balance. Just think about it for a second. He only decomposed the inside, right? He showed a symmetry that's held on the inside, hyperbolically defined, beautiful, but there's no symmetry on the outside that's made up for it, right? We're just decomposing the inside. Also, imagine coloring all this fluid that's moving around and twisting and folding. Every point where there's a twist happening, a hinge point, would need to have a unique action being described, right? So none of that detail is really in his picture. He's got a general geometric symmetric argument that gives these constraints in geometry. Great starting point, but we need to go further. Okay. So Thurston's decomposition was a brilliant addition to our knowledge of the hyperbolic figure eight knots geometry. But it didn't tell us everything there is to know. That is, it wasn't explicit enough to define every feature of this minimal geometric balance. For a complete understanding of the hyperbolic figure eight knots geometric properties, to sharply define its boundary conditions and every unique property of its balance, we need to go from generally decomposing its internal complement volume to explicitly decomposing its complete partition balance. All right, now if math is the thing that terrifies you, I'm trying to do this in a way that guides you in a way to show you how exciting math can be. So don't get scared by any math you see. Pick up whatever you can, and you can go over this many, many times, right? But try to follow along. It's certainly going to be worth it. Chapter 1, the minimum partition balance. The hyperbolic figure eight knot decomposes into 5 unique geometrically bound balances. To dive right into understanding this partition, let's look at this picture. On the left, comprising balance 0 and balance 1, which wraps around balance 0, that entire region within the white circle represents the white circle represents the cross-section of the surface we saw before. Okay, of the hyperbolic figure eight knot boundary, the complement volume boundary. Okay, so We have the inside on the left, and at every point externally from this balance, there is a unique counterbalance action happening, right? The blue counters the internal blue, the external red counters the internal red, and the external domain then ends up being the total sum of the two blue and red rotations externally, right? The combined sum of them. So balance 4 is just the actual orthogonal composite of balance 2 and 3. Okay? So each balance is a different rotation. You see, you can represent by a circle in each case. The circles are all connected. For the full picture, imagine on the outside at every point there's an action that counters the internal actions, right? So surround the entire white circle with this arrangement. Okay, so that's a basic partition separation we're showing there. Okay, it's not to scale at all, but it's the simplest way to just show the difference in partitions. Okay, moving on to the next picture, and the big thing you notice here is the combination. So the external domain that rotates under the purple that's rotating at an angle, if you're in that domain is just the combination of balance 2 and balance 3. All right. Now, to turn this into our first representation with numbers here, we can take these balances, which we know pictorially what we're representing up top in that picture, right? We have balance 0 through 4. And balance 0 is the smallest scale at the bottom, representing the smallest cyclic action that this balance represents. Okay, so once this balance is formed, it perpetuates 5 different scaled actions that are always present. Okay, all 5 of them are different sizes. So starting from the bottom, balance 0, the smallest scale, it's composed of an inner action and an outer action. Meaning if you draw a circle for balance 0, that circle represents the balance line of the balance. So on that line, balance 0 applies. There's an interior and an exterior of that balance. The interior action will be some unique action, and the outer rotation will be a smooth rotation balancing against that interior action. This union of actions must be making use of the derangements in this balance. We're using a different set of hinges in each case, different arrangements, so a different set in each case are doing a different set of things. And the total collection of all the things that are going on, all the divisions and balances, close repetitiously over and over and over, so that you could find a place in this balance that always gives a cycle of 5 different sizes. Since each balance has an inner and outer action, we can just write the general structure in this form. Now, it turns out we know some specifics already, because there has to be a projected reference scale in this balance, right? Somewhere in this balance is going to be the 1, the reference frame. So the reference frame is going to be the external domain. We're going to be in the external domain. So the reference frame is the center of the external domain. Now remember, the external domain is composed of the 2 external actions, balance 2 and balance 3, right? It exists because as a union of those 2. And those 2, balance 2 and balance 3, exist as inverses of balance 1 and balance 0. Right? Okay. Another thing to distinguish here, its boundary, since balance 4 is the reference, its boundaries are what will be balanced with the other balances. Okay. Because it's projected as the reference. All right. The balance point of the external domain, balance 4, prescribes the unitary scale of this decomposition. So 1, the scale of stability projected under this action. Under this ideal inversion, the boundaries of balance 4 keep balance with the other 4 balances. The action of the hyperbolic figure 8 knot is localized. That means it's not infinite. Okay, so it's contained to a finite amount. It's localized. Therefore, the rotations of its internal and external parts have to balance. So it has an external limit. So all the things that make it up must internally balance, right? If they've got a cage that externally bounds them, the actions within that boundary must be balanced, symmetrically balanced. Since the internal partitions of that balance are arranged under ideal split factorization, which we can represent as the derangements of the rotations, which is, the derangement would be exclamation point times by the number of rotations, which in this case is 5. So the red n in here will always be a 5, okay? Because this divides under 5 actions. And now we want the difference between that and its next expression. Its break and scale symmetry ends up being b here, which will always be 7. But at this point, you don't need to know that yet. So b times 5 is 35. All right, so the derangements of 5 equals 44, and then 7 times 5 is 35. So 44 minus 35 is 9. Square root of 9, 3. All right. Since the internal partitions of that balance are arranged under ideal split factorization in this specific way, the external partitions must be arranged as squared and doubled expressions of those internal actions, right? They have to be inverted. And since there are 3 external actions balancing against 2 internal actions in this geometry, the external expressions of that arrangement are its unique phase expressions, right? The 3 expressions, -1, 0, and 1. So I'm saying that if we arrange the hinges of these actions, so we've broken up our general decomposition map of the hyperbolic figure 8 knot, the 5 different actions that are in play together to make this form. And now we're just discussing the structure of the hinges, the derangements of each action, the derangements participating in or defining each action, okay? The full derangement structure is, of course, going to be just exclamation point n, right? That's the definition, derangements of 5. There's 5 actions here. So derangements of 5 is 44. The next scaled up expression of this is going to take use of the 5 boundaries, the 5 actions again, but this time times by the break and scale symmetry. And since it's a circular construction, break and scale symmetry happens to be 7, but we'll get to that in a bit. The internal actions, the 2 different internal actions, are making use of a different amount of hinges. The first one that defines all the available hinges, the full derangement set, 44, is everywhere. It's on every single hinge available in this action. The next action, though, is it's using as its centers 35 of those 44 hinges. It's a larger scale action that's compositely built and only uses 35 of the 44. So this difference in action externally, since it has to be balanced invertedly, right? Since it's a double cover on the inside and a split cover on the outside, meaning the action outside gets split. There's 2 things that divide the action, okay? That means that we're going from a 2 to a 3 exchange here, from internal to external, and we're inverting instead of going from double cover going to split cover. So we have to take our internal hinge actions, our square root of 44 minus 35, so it ends up being a total of 3. But then we have to put that total arrangement under 3 different expressions, -1, 0, +1. And then resquare it and double it. So externally, we're going to be arranged in a square and double fashion. Internally, okay, that's in the split cover externally. Internally, everything's going to be a double cover, right? The simplest possible double cover of the simplest possible manifold of 3 manifolds, the Gleesking manifold. Let's continue on in a little more detail. This localization symmetry updates the hyperbolic figure 8 knot decomposition map to this new form. So we can fill in everything on the right side of our equal signs, right? We can put in all the hinges of action, and we can be more specific about the external actions and turn every outer rotation into just an expression of rotation. So e to some amount, a variable. So we're going to here phi 0 through phi 4. Okay, so that's a lot more specific, but now we need to geometrically define the internal actions, right? To complete this decomposition, we must specify its balance of interactions. Let's begin by defining the absolute minimum cyclic expression, balance 0. So this is the smallest part of our balanced action. We have 5 balances of different size playing a role. We're going to talk about the smallest of those. Now, since it's the smallest of those, it's a very specific one, a specifically important one, right? This is the minimum possible self-balanced manifold that you can form under wave action that closes and continues perpetually, right? And this is the smallest cycle of that action, making it literally the smallest possible self-balanced cycle expression. Chapter 2. The minimum limit of persistence. The minimum cyclic action of the hyperbolic figure 8 knot defines the minimum possible cyclic action. A circularly closed action, pi r squared, trivially balanced against an external counter rotation. So e to a rotation of some amount we'll define as phi sub 0, which right now is an unknown. Okay, so you shouldn't know what phi sub 0 is. It's a variable for us. We're going to solve with this equation. So far our equation is just the smallest possible cyclic balanced action is going to be defined by a circle, pi r squared, and an external rotation that's countering against that circle. All right, so e to some variable. And that's going to be equal to our full derangement set. So all the smallest possible derangements of this whole structure, which will involve the derangements of all 5 boundaries. Well, if this is our equation, the only thing we need to now to solve for our unknown variable or external rotation is to define our radius. So, to represent this minimal action, factoring into rotations that counterbalance under ideal complex division, so splitting into equal but opposite internal rotations, each absorbing half the input, we set r equal to the hyperbolic sine function. So just the literal hyperbolic sine function. And to get a little insight what we're doing here, we're defining a cascade structure. Okay, so we have a hierarchical scale structure already. And now we're defining how the waves divide and get split at each boundary in this hierarchy. We're on the smallest boundary right now, and the smallest boundary divides under perfect, ideal hyperbolic balance, defined by the hyperbolic sine. Literally, we're going to put r now, so the radius of our circle is hyperbolically structured. So we're going to replace r with the hyperbolic sine. All right, but the hyperbolic sine has an argument itself, right? It's not just a fixed number, it's a thing that has a changing output based on its variable. Okay, it's also a cyclic output. Well, what do we want our variable to represent? What is this split division doing? It's balancing and splitting our action, right? So as we set the argument of this action, in order to represent our system, we're going to set the argument of this action equal to the minimal representation of square split division. Think about what that means, square split division. So a number that constructively possesses complex fourfold symmetry. Square split division. So some number squared, split division, so cut in half. So the number is going to be 1/2 squared. And 1/2 squared is 1/4. But since what we care about it is that it's squared and split, its structure, look very closely, 1/(-2) squared is also the same, right? Or -1/2i squared is the same, or -1/(-2i) squared is the same. So all 4 of those represent equally the condition of split square division, okay? So our argument is going to be, pick one of those. It doesn't matter which one. I'm just going to go with the first. Okay, and as a little quick aside, if you're more comfortable with talking about splits and divisions and rotations all in the terms of E, hyperbolic sine is defined that way. I'm going to stick with this form because I think it might be less confusing to more people, but we shall see. I mean, in the end, the notation needs to be something everybody absorbs. We're just talking about the cousin of cosines and sines, right? This is the hyperbolic versions of cosines and sines, which of course being balanced with the circles. So hyperbolas and circle unit balances is what we're talking here. All right, continue. Plug in this ideally hyperbolic balanced R. So the one we've defined here is hyperbolic sine of 1/4 or 1/2 squared, okay, into our equation. So plugging this into our equation, we arrive at the precise characterization of the minimum cyclic limit of persistence. This is really something to pay attention to. We've just arrived at the precise characterization of the minimum cyclic limit of persistence, the smallest action maintained by the square split division balance of the hyperbolic figure 8 knot. Okay, this is the smallest cyclic action possible. Beautiful, simple, elegant, short equation, but now there are no unknowns because the only thing we don't know in this right here is our external rotation amount, which so we can solve. All right, and you solve and you get this number, okay, and this number now represents the magnitude of the external rotation that balances this minimum cyclic action. All right, so we've characterized now one of our 5 geometric actions that define the hyperbolic figure 8 knots total balance. Great, we made a lot of progress. Now, if all of this was just a whirlwind and every time you see a hyperbolic sign, your brain shuts down. And a lot of people are afraid of math. But I'm trying to help follow through this so that you can at least follow along, and while you're watching it, kind of get more familiar, right? So notice, well, first, mathematics is the language of relationships, literally, right? Everything in math is defined by how it encodes a relationship. That's what it's employed for. So to be able to read mathematics is to be able to read in a language of relationships, a language that goes far beyond the language that you find in the common tongue, right? The things people talk about are so far diminished compared to what you can talk about when you open up to the language of relationships. This balance that we've been talking about balance 0, is perfectly encoded by this language, by this geometric balance, right? This structured balance. We have something split in a squared way, or orthogonal in 2 ways, right? It's under the ideal hyperbolic sign balance in a squared orientation, circularly arranged. So closed to circle. Beautiful, beautiful, simple, elegant, as simple as they come, right? You can write this one right in the palm of your hand very, very simply. Why does this matter? We're going to get to that, but just follow along even if the math is still confusing or scary, because I want you to see how you could just plug this number into the computer, right? Go to Wolfram Alpha, type in pi parentheses SINH, right? Just type in the equation just like this and put an X for the variable after E, the rotation amount, equals exclamation point 5. Okay, just type that in and it will solve for your variable. You'll verify for yourself. Cool. This number represents the number that balances externally with this structure, this geometry. Cool. Now, this equation defines the minimum partitioning that can be balanced under locally closed cyclic action. So if it's something that persists, this is the minimum possible partitioned expression of persistence. Let that sink in a little bit. Try to imagine the depth of what that means. It holds the honor of being the ultimate boundary condition, the absolute minimum limit of measure, beyond which the possibility for persistence itself is operationally cut off. In other words, this equation describes the minimum boundary of time. Okay? I'm hoping this is kind of clear. If you think you just misheard me, let me say it again. This represents the smallest cyclic action in the smallest possible self-balanced geometry. Therefore, it represents the smallest possible boundary condition in the smallest possible simple universe there is. Beautiful, beautiful geometry. But we've got 4 more conditions to explore before we've got the whole geometry in our head. So let's take another look at this. We can put a complex representation to get a picture of what's going on. This action is dividing the world, flipping and twisting it, right? Cutting it in 8 directions. Beautiful. You can see the complex plots here. Anyway, take a look at these equations. Balance 0 can also be written in both of these forms. I particularly like this square root of I over 2, 1. Maybe one of these pops in more for you than the other, but take a look at the elegance of each. They're all equivalent, okay? Go up to the first one and compare them. Maybe you can see the balance that it's defining. It's really important to have that kind of sink in. And to kind of understand that this number, the phi naught number that it kicks out, represents this balance. It refers to this balance. Chapter 3, the first consequence. Under this construction, the highest resolution of cyclic action, the smallest scale, refers to the smallest closed loop, represented two-dimensionally as a single circle, right? Okay, the one we already covered. So now zooming out to the next available scale, one step out in resolution meaning in a world built from those smallest pieces. The next size circle we can construct from those circles is comprised of 7 elemental circles. So 6 outer circles surrounding 1 inner circle, just like in this picture, right? And the negative space that divides them. Therefore, the break in scale symmetry between the first and second scales of circular construction is always going to be 7 in this, because it's circular construction, okay? So B, or blue B for the rest of the book, is going to be representing exactly just the number 7, 7.000000000 all the way, okay? And this is why. We're talking about the break and scale symmetry. So if you have an action balanced on the center circle, it's in some communication with all 6 on the outside. Okay, so it goes from being an action on one scale, if it's all located on the inside one, to communicated an action that has to be now spread over all 7 on the second scale. Okay, I think that's easy to follow, but if not, just keep trying to follow along. If you get 10%, I mean, it's a great way to be introduced to a topic, right? If the learning curve's steep, then they get more to learn. Great. With this in mind, let's zoom out to the next balance of this hyperbolic figure 8 knot, so to balance 1, whose inner action is the operationally rotated inverse action of balance 0. Of course, because it's in connection with, it's defined with it, right? So adjusted for the break and scale symmetry between the two balances. So balance 1 is going to now maintain a new external rotation. A different rotation comes into play from this scale on out, okay? A rotating over sync of now, remember, 7 times 5, 35 of the fundamental 44 hinges. Okay, so at this scale, those 44 hinges now have 35 of those 44 hinges have now acquired another additional rotation, all in sync together, but just 35 of them. All right, so here's our equation for balance 1. It's the inverse hyperbolic sine of, it's operationally rotated, so now we get to put the sine of the sine in order to be perpendicular or orthogonal. The hyperbolic sine of the hyperbolic sine of 1 over the break and scale symmetry. And now the external rotation that balances this is equal to 1.616259181 on. Okay? So getting the picture here, we're defining the geometry, the geometric action on the inside, the rotation externally outside of each balance. And we can then define specifically numerically the value of that rotation that makes this balance. Great. We check out the plots again, of course, but let me guide now. Those are really beautiful to look through. Actually, let's talk about the plots. If you look at the plots, these are really helpful. Remember, we're distilling one of the 5 actions. Okay, what does this one action do? This action looks like it's twisting and folding things up in a very specific pattern, right? And it's really useful to look at both versions of the pattern. The twisting and folding becomes very, very obvious when you have the imaginary plots with the complex plots involved. Okay, so that's really worth some intuition time, but let me continue for now here. Balance 0 and balance 1 trivially maintain an arrangement of squared partitions, so the boundaries are squared, okay, under this arrangement, and that arrangement's also, those boundaries are also orthogonally factor under ideal hyperbolic balance. The gamma function of n, the 5 boundaries, is what we mean there, okay? So look, orthogonally at the same time, so in 2 orthogonal ways, we have an arrangement of boundaries that are squared and perfectly, ideally hyperbolically balanced. So they factor under ideal hyperbolic balance, right? Beautiful. And if it's the first time you've ever heard of the gamma function, you're going for a fantastic explosion of surprises. A lot of people from the physics background may have never heard of it unless they get really, really, really high in theoretical physics. But it's a very fundamental function. Moving on, chapter 4. So far we've described two of the balances that make up the hyperbolic figure-8 knot. Okay, we described the two internal balances. Now we're moving on to the external balances. Within the external domain of the hyperbolic figure-8 knot, the boundaries of balance 2 and balance 3 are put into mutual ideal hyperbolic vortex arrangement. I want to think about this real bit. They have to be the inverse action of the internal arrangement, right, to be balanced. And they can't go off to infinity, so you know that there's going to be a vortex. It's going to be a closing loop. It's going to be hyperbolic, and it's going to circle, or it's going to have a circular external bound. All right, we're going to get more to that in chapter 6. For now, let's notice that balance 2 forms the vortex's throat. Okay, so that defines where the 5 unique partitions of the hyperbolic figure-8 knot doubly periodically divide. So there's constant in math we can ascribe to that, called the Weierstrass constant. We'll get that in a second. While factoring along the break and scale symmetry of the geometry. The break and scale symmetry was the B, the blue B, which is 7. And since we're factoring along it, we're just doing the square root of 7. Okay, so we have a wave action that is being divided. We have these wave actions being divided, okay, doubly periodically, and wrapped around the break and scale symmetry. They're divided by that too. And one other thing, remember they're a vortex, so they have to be wrapped axisymmetrically around a pole. Right? A vortex needs to wrap around a pole, which means it singles out one of 3 dimensions as important. Cool. All right, now this balance has an external rotation of phi sub 2, okay? And if you remember its hinges, it's going to be 3 plus 0 squared, okay, times 2, so 18. Now we can calculate the value for that rotation, right? The equation now, just like before, we're done with it really, but I want to develop a little more on this one. So we're just kind of doing a little side step here for more instruction, because I want you to know what this Weierstrass constant is really about, okay? Because we didn't explain it yet. And that's the confusing thing in this equation. Everything else is extremely simple, right? Okay, so here we go. The Weierstrass constant is the constant that describes the unitary balance of the Weierstrass sigma function. So like the unitary circle equations and stuff, okay? So this is a unitary sigma function that you can see from the structure of the way we represent the function, 1/2 sigma of 1 versus 1 comma I. So a unit thing interacting with a unit 2-dimensional thing. Cool, right? It's really, we can kind of read that into the structure of that representation there. Here's more specifically. The Weierstrass constant very exactly is 2 to the 2n, so we get a double covering of e to the pi, and both of these things are raised to 1/8. So think of this as the being dragged by 8 hinges. Now on the right hand side then we get the gamma function of 1/2 divided by the gamma function of 1/2 squared, whole thing squared, right? Okay, this is just the definition of the Weierstrass constant, but I want you to see the symmetry going on here. First of all, the gamma of 1/2 is the square root of pi, so you can pull that out if you're more familiar with the pi, but it's nice to see the combination. We have a gamma splitting, a hyperbolic balance splitting, divided by, so one splitting divided by a squared splitting squared. You see how that's going to fold back on itself in 2 different ways? So this division process guarantees that whatever we're talking about, whatever it's applying to, which is on the left, the double cover of the hypersphere, beautiful, okay, that has 8 hinge points in it, very related to the 8 geometries. All right, the unitary Weierstrass balance defines the harmonic double cover projection of the n-dimensional hypersphere, all the even numbers, okay, internally divided over 8 partitions and maintained under lemniscate balance. So lemniscate balance divided by this 2 times the square root of 2 of the lemniscate constant. So there's another way of writing the Weierstrass constant. e to the pi is the infinite sum of the even-dimensional harmonic volumes, which follows from the fact that equations for the volumes and surface areas of n-dimensional hyperspheres of radius r are these equations. So since we have the equations to any dimension, you can just put in all the n's and you can get a series now. And that series ends up being this series, right? Based on the gamma function or the factorials, right? Okay, so this gamma function is a central player here. All right, let's continue on. The lemniscate connection here. A lemniscate is a geometric shape. Here we go. There's a lemniscate shape. But alongside the balance of this unitary Weierstrass sigma function, it's associated Weierstrass elliptic function. So it has many faces. Okay, it has an elliptic function face. Orthogonally maintains a balance with equiharmonic, lemnistatic, and pseudo-lemnistatic expressions. So it has all of these, right? So we look at the frequency of each. We get omega 1 and omega 2, and they are defined in terms of the gamma function, okay? We get the lemniscatic half periods, as you can see in the imaginary direction and not in the real direction, the lemniscate over 2 times the square root of 2, and the pseudo-lemniscate half periods. Also, again, an imaginary arrangement with the lemniscate constant. All right, I'm hoping you're seeing the beautiful symmetry happening here, but all of this structure is in the same system, okay? These are all orthogonal representations of the balance maintained. So that you can see it's a unitary, very simple, beautiful, but rich balance. All right, the lemniscate plays a central role, a quadruply orthogonal role in this balance because the lemniscate is the inverse curve of the hyperbola with respect to its center. Instead of writing balance 2, which we've defined already in terms of the Weierstrass constant, we can also define it directly in terms of lemniscate constant, clearly, right? But for now, let's write it in terms of the gamma function, because I want to highlight how this boundary, this balance, is maintained under ideally squared split hyperbolic balance. And it's really beautiful to see that, because compare that now to our first balance, the balance 0. Remember, the structure of our very first balance was split square division, and this is hyperbolic split square division outside. Great. Balance 3 defines the opposite end of the hyperbolic vortex. Think of the back end, right, where it all circularly closes. So where the partitions of the hyperbolic figure 8 knot circularly close, 2 pi n, okay? Circle is 2 pi. We're going to take all 5 of our rotations and make them so that they circularly close, while being squarely balanced on the internal split division of our hyperbolic figure 8 knot, okay? Now, this thing's squarely balanced circularly, so we're going to do a cosine of our break and scale symmetry over our 5 rotations, or 5 actions. Okay, great. This one, of course, if we refer back to before, has 8 hinges in total. This is the last external expression, right? As we're coming from the internal world to the external world of our hyperbolic figure 8 knot balanced environment, the vortex closure reaches out to the last expression of this. As far as everyone's concerned outside of that, there's no magical domains or actions happening. It's just the presence that's magical to begin with, right? It's just projected without explanation. Here we're provided an explanation. We've got the entire purple domain projected by the balance on the boundaries on the inside, right? It's projected by and made in the middle central scale, which, by the way, it represents 1. The central purple dot in the middle of the central, or the purple circle, represents a scaling factor of 1. 1 what? 1 compared to all of these measures. Every measure here would agree that that's 1. That's the 1 for each measure. And the cutoff for every measure is going to be a very specifically defined thing, but they all agree and they all project this as the central stable scale, the reference frame, the 1, okay? The balance point of the external domain, so balance 4, prescribes the unitary scale of this decomposition. 1, that's what I was just saying. The scale of the stability projected under this action. Great. The internal boundary of balance 4 is maintained by logarithmically factoring under, you guessed it, ideally squared hyperbolic balance, right? We have to counter everything we've done. So now we can just write down the same circular structure that has to be balanced on, and we can invert this into hyperbolic cosine of boundary splitting. Okay? The 2 cosh log b can also be rewritten in many simple, elegant, easy ways. I'll let you play around with that. It's very straightforward, right? We're just talking about the hyperbolic cosine, the natural log of b. So, by the way, yeah, log, I'm just meaning natural log. When this balance is achieved, then the universe within it is under these 5 rotations, but also the universe within it is cut off with a minimum action. You can see that minimum scale on the left there. It's where the arrow balance 1 is pointing, but it's the radius of edge of balance 0. So the furthest scale reach of balance 0, okay? And it goes out that way for each one. The external boundary, so the inverse boundary of 4, inversely expresses the action of boundary 4. Big surprise. But this boundary defines the outermost edge of action. Okay? In the whole cyclically defined universe of the hyperbolic figure 8 knot, this is the edge of action. It's the other boundary across which no action participating in this balance crosses. Right? There's no wave energy that's maintaining this balance that crosses that edge because it's the external boundary of it. Great. So it inversely represents the action of the internal one, though. Okay, beautiful and simple. So those are just inverted. Now, by fully decomposing, by the way, we're done. We've decomposed all those actions. We have geometric expressions that are balancing hyperbolically and cyclically and logarithmically. It's a perfect, elegant, but complex. It's not just 2 parts, right? It's 5 complex parts. All right. Well, now that we've fully decomposed this partition balance, the partition balance of the hyperbolic figure 8 knot, we've mapped the most elemental balance possible, defining the simplest possible persistent stage. So that in its own is a beautiful reason to be interested in this, because it elegantly defines the smallest concert of actions that can exist in a self-balanced stage in a universe of persistence. Okay? So in anything in which there is a domain of physics, anything that can be studied, any property of persistence, the minimum condition is that the hyperbolic figure 8 knot has been met, that it is persisting. So that all 5 of those balances we just worked out are under play. So now everything we've said so far can be summed up on this next page, the complete partition balance of the hyperbolic figure 8 knot. All of those equations all at once, right? Just structured like this. And when you see them all together, it's really worth spending some time, because we're talking about the most elemental balance structure possible, okay? But as you're going to see, there's even more reason to really spend some time absorbing this balance, this structured balance, okay? Because if you scroll down to the bottom of these, we've listed out the values of the different external rotations. So from external rotation 0 through 4, okay? We've listed out several digits, and we're listing the derangements that each one is active over. So the 0th rotation has a value of 5.391258 and so on, and it's active over 44 derangements, okay? And so on up. So we have these numbers and this list that represent the hierarchical structural action of the hyperbolic figure 8 knot. Great. We'll move on now to chapter 5. In what is it, 1 page, or do it 2 pages? 2 pages. We're going to now completely switch directions. So far we've been talking about geometry, right? Just geometry. There's been no actual connection to the physical real world. We're just defining the simplest possible geometric balance, and we're being nitpicky about defining every single balance individually. So we've divided it, decomposed it into its individual balances, right? Well, things are about to change. Chapter 5, the boundary conditions of physical reality. The boundary conditions that maintain the balance of the hyperbolic figure 8 knot define the boundary conditions of physical reality. the measured limits of time, space, charge, mass, and temperature known as the Planck constants. And I mean this directly and literally. Every persistent external rotation of the hyperbolic figure-8 knot, which we just defined, multiplied by a boundary doubling in each case, raised to the number of hinges synced to that rotation, defines a bound of physical measure, a Planck constant. So let's look at the bottom here, the Planck time, the minimum possible time available, not just because of our limits in technology right now, available in nature, we have found is equal to 5.391247 plus or minus 60 in the 47 times 10 to the negative 44 seconds. And here, in our geometric structure, in our balanced decomposition representation of the hyperbolic figure-8 knot, the minimum possible balance, we find that the minimum expression in that balance happens to be equal to 5.39125836832331 and on times 10 to the negative 44. It's exactly within the error bars of our best known measurement for the Planck time. And in every single case, the 5 dimensions that make up our physical reality, the measured limits of each dimension is predicted by, and now to any digit you want, the structure of the hyperbolic figure-8 knot. Just look at this on one page. Those 5 rotations define the 5 boundaries of physical action in reality, the 5 dimensions of our universe, the boundary conditions of reality. It's beautiful. And now, that means we know these values theoretically, right? We now know the Planck mass. We know what its true number is, what its true expression is, and why. Beautiful. We know what all of these are. But what does this really do for us, other than explain the Planck values, which have had no story or no explanation until now? What else can this really do? Well, let's see. You might have a suspicion at this point that now that you've framed the boundary conditions of reality, we can really do some physics. Since, if you've had any physics background training, you know that physics is generally something that's defining a system, defining its boundary conditions, and then you're basically done. Once you've finished defining your boundary conditions, you know what the system's going to do. Right? Well, we've never had the boundary conditions of reality before. Here, we've just got a simple, single geometry that perfectly, identically, geometrically, and numerically predicted perfectly the conditions of every limiting measure of our physical reality. Fantastic. The hyperbolic figure-8 knot defines a bounded arena composed of 5 persistent kinds of measure. We're going to call them time, space, charge, mass, and temperature, just to go along with our historical tradition, okay? But it doesn't matter what we call them. The point is that there's 5 persistent kinds of measure whose boundaries are the Planck constants. The Platonic form of persistence, the simplest possible self-balanced manifold, elegantly and uniquely defines the stage of reality. I think this is more elegant than words can ever approach. Look at this system, the simple inside-outside balance that we're maintaining here gives us a partitioning that defines the Planck time, the Planck length, the Planck charge, the Planck mass, and the Planck temperature as the grandest reach of each of those 5 actions. Chapter 6, the hyperbolic vortex. All right, we're not very far off from all the math you really need to put everything together. Right? We've gotten the decomposition structure of the 5 actions. Now, I want to talk about all the possible expressions of charge and mass in this balance. So the external Planck charge boundary and Planck mass boundary are connected, of course, right? You see that they're always bound. But I want to know how many possible ways can they be divided up? How many ways can we divide up this charge and mass boundaries? Right? These 2 actions are in play, they're in motion together. So how many partitions are available in this action? All right, well, to do this, we start with recognizing that the 2 external boundaries, the hyperbolic figure-8 knot, the Planck charge and the Planck mass boundaries, connect via the hyperbolic vortex equation. Now, I know if equations aren't your thing, try to suspend that for this one. because this is one of the most beautiful equations you will ever see. I mean, honestly, this whole book is literally the list of most beautiful equations you'll ever see. First, you start with just the unit hyperbolic equation, 1 over x plus x cubed. Okay, you set it equal to whatever you want, depending on the scaling you want to make this thing. Instead of just having the hyperbola equation, modify it so that the third one gets wrapped around a circle. Okay, so it's almost the same as the equation you're so comfortable with doing a hyperbola, just the base hyperbola. Okay, and I'm using je instead of x, but it's just a variable. When you set that structure up, instead of a hyperbola, you have a hyperbola whose third component is wrapped around a circle. The component that's not a simple inverse of the other, right? So 2 components are just inverses of each other, really awesome. And the one that's not is wrapped around a circle. Cool. Well, now that we have that structure just geometrically arranged, we just define a relationship. We have 2 things that are opposites and one thing that's cubed and wrapped around a circle, right? But we're going to set that equal to the geometric action of our hyperbolic vortex, which, as you can probably guess, is twist and twist, 2 different orthogonal direction twists. So 90-degree twist one way, simultaneously at the same time, right? 90-degree twist another way. Okay, you can write this as e to the negative pi over 2 and then raise that negative pi over 2, or e to the negative pi over 2 is equal to I to the I, so I'm going to write it like that. So 2 twists of negative pi over 2. Minus the boundary you're twisting around. So wherever your 0 is, your 0 line. Well, since we're talking about the action, the hyperbolic vortex that connects the boundaries of the charge and mass boundaries in our hyperbolic vortex action, right? So we're going to subtract the Planck mass boundary from our equation. Very simple, elegant, with just taking a hyperbola, a unit hyperbola, wrapping one component around a circle, and setting this construction equal to 2 twists around a 0 boundary, specifically the Planck mass boundary. Now, when we do this, we can just put in the computer and solve for our variable, and we get the partitions of this arrangement. We get the solutions. So this connection partitions into 4 solutions, right? It's a cubic term, so it has to have at least 3. It has 4, and they're composed of 6 parts, 4 real and 2 imaginary. If this is a completely new topic to you, try to follow along. We're saying that the geometry of that equation divides things up into segments that have a slice of this first number, je1, 0.08542, on, and je2, and je3, and je4. So simultaneously, all of those values, every one of those numbers, you could plug into our equation up there as je, and it would give you the correct answer, right? So all 4 of them are perfectly valid solutions, which means they represent all of the natural partition divisions that are now balanced between the Planck charge and the Planck mass boundaries. They represent the way we divide up charge and mass. Very important. Great. These solutions have ideally cyclic combinatorics. This is something we really should spend some time on. I kind of blow through it because I really want somebody to see the elegance here. So I would try to streamline and make it short. But let's pause for a second. If you take those 4 solutions, you can see what their values are above. Multiply them all together, you get 2 pi. If you add them all together, you get 0. And if you square them first and then add them, you get negative 4 pi. This has a combinatorial arrangement with a circle, a balanced point at the middle, and a projection of a sphere, 4 pi, the surface of a sphere, projected, negative, right? It also maintains a twin and a reflection relationship and 2 pairings. This is like, the partition relation here is the most elegant thing you're ever going to see. We're connecting a summation and the product of our j's. So the sum of j's squared and the product of j's squared are identical, except for the factoring of negative pi on the sums. That's beautiful. Really beautiful. Okay, continuing though. And I don't want to scare people with the math, but if you look at the math, it really is worth your time to look at the structure that the math is trying to convey, because the relationship in the math is telling you how nature is structured, is telling you literally what's going on. So avoiding the math is avoiding the conversation, honestly. This book is meant to be the most streamlined discussion, story explanation of these parameters that's ever been. Well, there's never been one before. Nobody's ever explained numerically or geometrically any of these parameters. But I also wanted this to be a short introduction to it all, so we'll streamline it. All right, since these solutions define the connection between the Planck charge and Planck mass boundaries, they define the natural partitions of charge and mass. Okay, let's keep that in mind. Now we'll move on to chapter 7, charge partitions. So remember, charge now refers to the Planck charge boundary, a specific action in this balance. You don't have to think of charge as some magical zapping thing. It's literally just a specific action participating in this balance, and it has a boundary. Okay, it always has the same boundary because this balance is always minimally there. All right, so now we're going to be concerned with how many ways can charge, the action on the charge boundary, be presented here. Remember, it's tied up with the hyperbolic figure 8 knot, right? It's literally bounded right there, so it only has one expression that it can continue to do, but it might have three orthogonal. You might not know how many ways it's going to show up, right? How many partitions does it maintain? So when charge is externally present, so in the external range, wherever the charge the boundary happens to be at. So it's never going to be an action that you say is at the Planck temperature boundary or the inverse Planck temperature boundary. And it will have a value of 0 there. But at the Planck charge maximum reach, its magnitude is equal to the Planck charge boundary, right? Multiplied by the first solution of the hyperbolic vortex equation, because it's under hyperbolic vortex arrangement. So the first solution nabs right at the boundary there and says, okay, we take the charge boundary and we twist it exactly into the hyperbolic vortex, and there we've selected the elemental charge of reality, the electron's charge, exactly to every significant digit within the error bars. Perfect, beautiful, one of the most beautiful equations ever. Because now we know what J1 is, right? It's just the first solution of the hyperbolic vortex equation, which defines the partition connection between the charge and the mass boundaries, which are 2 of the 5 total boundaries that make up the balance of the hyperbolic figure 8 knot. Beautiful, simple, elegant. I know it's complex, but it's the simplest thing that's ever been imagined that can contain the complexity we've actually observed. Let's continue. Internally, this charge partitions exactly as the volume of the hyperbolic figure 8 knot partitions, right? But in the imaginary direction. Now, we haven't said this before, so this will be new, but it's into negative 1/3 and positive 2/3 action of a dilogarithmic flip. How do we know this? Because there's a definition of the volume complement of the hyperbolic figure 8 knot that is this equation here, I times 2 dilogarithmic parts of a flip, so -1 means flip, right? But one of them's positive and one of them's negative, and they don't get to be full flips. One of them's a 1/3 flip, and the other one's a 2/3 flip, and they're in opposite directions. So -1/3, positive 2/3. Great. And this defines the structure there. So this partitioning of -1/3 and positive 2/3 internally defines how charge gets to be presented, okay? How it partitions internally. So on the same structure. Great. So this arranges charge, the expressions of charge, into the following fundamental partitions. We have external partitions and internal partitions. And externally, you're always wrapped into the hyperbolic vortex. So you're always taking the Planck charge boundary and multiply it by the first solution of the hyperbolic vortex equation. And you can go in either direction, so it can be negative or positive, but it's always going to be just that amount, okay? Or 0, if it's not present. So if it's not on a boundary where you can't have it, its expression, then it's 0. But internally, that charge is split up. So you take the -1 and you can split it into the -1/3 and the positive 2/3, okay? So internally, because the hyperbolic figure 8 knot is, in the imaginary direction, divided under that construction, its charge boundary reflects the exact same symmetry and has the same partition balance, which means this little snapshot picture shows you, in that one little equation, or these 2 little equations, show you all you need to know about the charge structure. Not all, you need a geometric picture and you want to see all the swirling and vortices, but if we're just capturing the numbers of them, we've captured them all in a simple story, right? We've connected the charge and mass boundaries. We've partitioned all the expressions of charge that show up in reality. as the only ones allowed in our construction. Really great. But all the charge expressions of the fundamental particles of matter have been geometrically arranged. There's many ways to do that. It's been done for a long time, right? So the prediction, in that sense, we can geometrically predict that construction. But what has never been done is a prediction of the masses. Well, I should back up a little bit. No one's ever predicted the charge of the electron. So that's the scaling here has never been predicted, but the arrangement between the particles had of the charge, right? Okay, so we've uniquely nailed the scale from our hyperbolic figure 8 knot decomposition structure. We've perfectly explained the charge of the electron that way. We've perfectly explained the way charge partitions in full, either exactly as much as an electron in positive and negative amounts, or it internally ends up being always negative 1/3 or positive 2/3 or the full negative 1. Great, moving on to the mass partitions. Now we get to do something that, well, I mean, we've done some seriously interesting things already, described the minimum boundary conditions of reality, and so far that's allowed us to predict all the way up to the charge arrangements of the fundamental particles of matter. What about the masses? Chapter 8, Mass Partitions. The mass boundary binds two figure 8 knot volumes in 4 orthogonal ways. Okay, pause for a second there. We are externally expressing, think of the shadow of action of the hyperbolic figure 8 knot, twisting and twisting and twisting, and always wrapping back into itself under balance. This inverted balance means that the external split cover domain orthogonally expresses this volume trace in two ways, right? Internally it's a double cover, externally it's a split cover. So the simplest possible way to talk about this, the shape of the mass boundary, is the following. The mass boundary binds two figure 8 knot volumes in 4 orthogonal ways and trivially terminates inverse hyperbolically over the derangement structure of the hyperbolic figure 8 knot. That's a big sentence. It's a lot to parse. But that one sentence written down in mathematical form below, where the mass of the electron equals 2 times the volume of the hyperbolic figure 8 knots complement, times by the Planck mass boundary to the 4th power. Think of this. The volume of the hyperbolic figure 8 knot is equal to twice the Gleason constant, right? The Gleason constant is the minimum of 3 manifold. Well, it's the figure 8 hyperbolic knot is a double cover of that minimum manifold. So a double cover has to go around twice before you get back, like going around a Mobius strip, okay? The Planck mass boundary, instead of being squarely associated now, it's associated with 2 of them that are both double covers. So the balance is extremely rigid in 4 orthogonal ways, okay? This action is perfectly maintained that way. And trivially terminates inverse hyperbolically, right? So this simple equation right here predicts the mass of the electron. This primitive tessellation of the mass boundary, the Planck mass boundary, defines the mass of the electron. By defines, we plug in the numbers and you literally get this prediction. 9.1093837016199 and on and on and on. As many digits as you want times 10 to the negative 31 kilograms. Remember, our stage defined the dimensions. It defines what kilograms are, and now it's picking a very special scaled size on that scale, right? The mass of the electron as a unique signature on that boundary. You follow me? So we're not just using the hyperbolic figure 8, not defining the boundary conditions, defining the boundaries of the 5 dimensions of reality. We're also now, under this structure, the first and foremost, for the mass boundary, the first structure it wants to fall into happens to be the mass of the electron. So accurately that it gets one of the best numbers we've known in all of science to every single significant digit and continues predicting more. Every green digit in this, by the way, is a predicted digit, so it goes beyond current measurements. The preceding black digits, anytime you see a green digits, and with preceding black digits, that means that those black digits verify the measurement, right? Green digits go outside of the prediction of the measurement. So in this case, we've measured that the mass of the electron is 9.1093837015 plus or minus 28 in the 1,5. That's our error bars. So the 1,5 are shady, we don't know for sure, but we're claiming the 0 is right, everything up to the 0. And the 1,5 is close to right, it's plus or minus 28. Cool, times 10 to the negative 31 kilograms. And here, we've predicted all those digits. We get all the ones that we knew right, all the way up to the 0 for sure, and we predict a 161994. Notice I'm not leaving the 1 as black because the 1,5 wasn't completely sure. Okay, so we're confirming with the 1 what we thought, but it was a sloppy thought in a way. The 1 and 5 we weren't so confident on. We confirmed the 1 was right. We showed the 5 is wrong. It's a 6, right? Anyway, the point is, look how accurate this is. Look how beautifully simple, elegant. This is so obviously true. It's like, must have been how when Dirac discovered how to do square roots of negative numbers by making things two-dimensional. It so obviously allows the geometric balance and then predicts what you need. His didn't have a scaling. He did everything unit-wise. Here, we've got a natural system that has a hierarchical projection. It emits a hierarchy of actions. And that hierarchy of actions divides and twists and balances, but its natural most expression on its mass boundary, the last expression within the external domain of this action, right, is perfectly defining the mass of the electron. Let this sink in a little bit here, because I'm not going to be, what you might be expecting here is then to come up with some completely unique in each way equation then that can explain the mass of every other thing and predict them. And that would be beautiful to have equations like that, right? But we're not even going to go anywhere from here. This tessellation of the mass boundary has different orthogonal expressions of it. This one mass boundary has many ways of being represented, or many ways you could break it up and say, from this angle, it's broken up and it looked like it's tessellated out of these pieces. From this angle, it's tessellated out of these pieces. And yet it will be the same boundary every time. I'm saying that this one mass boundary, the Planck mass boundary, is arranged such that the 17 possible ways you can look at it give you the unique 17 expressions of mass that make up the fundamental particles of matter. It's instructive to note that the reflection or external action of every inverted cyclic balance maintained within the hyperbolic figure-8 knot terminates on this specific boundary, the Planck length times by the Planck mass over the Planck charge squared. So that boundary arrangement exactly, okay? Because this is where the sum of its 5 external rotations collectively partition into the n hypersphere, so the total set of hypersphere of maximal volume. So if we take the sum of all 5 of our external rotations in that make up the balance of the hyperbolic figure-8 knot, so add all 5 of them together, okay, from 0 to 4, that equals this partitioning. It divides a sphere cubically, okay, under 2/3 square action, but inversely, it has a 3/2 squared action, so those things cancel, okay, when they collide. And notice the factor here is the dimension at which an n hypersphere has maximal volume. That dimension divided by those 5 boundaries literally sets then what? The hypersphere. We're saying that now our construction in total, when you have all 5 actions together, makes the dance of the hyperbolic figure-8 knot. It makes a universe, a stage that's under that balance. But externally, if you're only looking at the external part, the actions here communicate as being the hypersphere. The math is far less scary the moment you realize that every time there's a second part, a right-hand part in these parentheses, it says 1 plus or minus something times by those Planck length over Planck mass over the Planck charge squared. It'll always be that same external boundary. So this is where things end up, okay, on the external side under that arrangement. Okay, good. So now remember, we've got this mass boundary of the electron. We've got its primitive tessellation of the Planck charge, of the Planck mass boundary is the mass of the electron. And now, let's talk about the other tessellations of that boundary. So, first of all, it's a rule that any squarely balanced periodic hyperbolic space has a total of 17 possible tessellations, or tileings, okay? Always. There's exactly 17 plane symmetry groups. So to find all of the possible tessellations of the mass boundary maintained by the balance of the hyperbolic figure 8 knot, we orthogonally extend its trivial tessellation, the mass of the electron, under ideal balance of square splitting and joining, guaranteeing that, and just try to follow along here, we got 3 conditions, but they're already conditions you're aware of. 1, the Planck charge and Planck mass boundaries connect via the hyperbolic vortex equation, right? We've already stated that. But we're just saying this needs to be a condition that is maintained. 2, the balance of that connection squarely hyperbolically bifurcates, splits, in 2 orthogonal but otherwise indistinguishable ways. While, of course, this inverts the internal structure of how things are squarely split, right? While dilogarithmically persisting under unitary hyperbolic circular balance. Okay, so everything has to close. We're balancing hyperbolas and circles, but everything has to close. And since we know this dilogarithmic connection is internal on the inside, we know everything has to then be braided under a plus 2/3 and negative 1/3 internal split action. Braided under the internal split action of the hyperbolic figure 8 knot, right? Great. So we have one primitive tessellation called the mass of the electron. That's the primitive tessellation of the Planck mass boundary. But the tessellations that capture the square splitting and joining balances define now, they extend our definition of the mass of the electron, and then we can include the orthogonal representations here under that geometric arrangement, right? So we're forcing the arrangement in which the geometry squarely splits but then joins, just like a vortex. It splits in 2 different ways, but then it also is rejoined, right? In another orthogonal way. Okay, cool. So the tessellations that orthogonally capture this balance of square splitting and joining define the proton mass and the neutron mass. Let's take a look at these equations really quick. In both equations, we have the mass of the electron on the left, okay? On the top one, the splitting map, we have the mass of the electron compared to the mass of the proton, times by the second solution of the hyperbolic vortex divided by the first solution of hyperbolic vortex squared. And this is equal to our 2/3 action squared times by the alpha Feigenbaum constant minus 1 squared. Now, let's pause for a second. Alpha Feigenbaum constant, this is the period doubling bifurcation constant to the logistic map, right? If you're splitting, and we have square splitting, we're going to do a square hyperbolic splitting. So we're going to do splitting, make it hyperbolic, minus 1, square it, raise it to the second power. Everything on the top there that we've gone through so far is all squared. You can think of the square root of the mass of the electron, square root of the mass of the proton, and then squared on top, okay? Before we get to the right-hand side, let's compare this now, the left-hand side, to the second equation, the joining map. Here we have 3 parts on the left, the neutron, the mass of the proton, and the mass of the electron. We have the difference between the 2 up top divided by the electron below. The different arrangement, right? Not just a simple division, it's a subtraction and division. In this case, it's the joining map, and we get the 1/3 action. But this 1/3 action is doing what? It's joining a circle and a hyperbola. Great. Well, the circle is probably going to be the pi, right? The hyperbola is going to be 3. Think of the limited expression for as x approaches 1 when you have 1 over x plus x cubed. Now, as x approaches 1, that goes to 3, okay? The mu, though, might be an entirely new thing. This is the non-trivial zero of the logarithmic integral. So in the logarithmic integral, we have the 0, 0, the trivial zero, and we have one other zero. So there's one logarithmic set of bound zeros, and this relationship binds them. So what do you think of that saying? We have a circle and a hyperbola being joined under logarithmic bind, right? Yeah, good. Pretty getting simple, right? The more you stare at them, the more it pops out. Now let's look at the right-hand side. In both cases, we get an inversion, right? We get now the 1/3 action up top and the 2/3 action below. And here, we're getting a rotation of e to the 3 gamma in both cases. Really beautiful, negative 1/3, positive 2/3, both on the rotation of e to the 3 gamma. Think of gamma as the splitting coefficient. Okay, not the alpha Feigenbaum splitting coefficient, but let's think of it as the braiding coefficient. That's a good way to go about it. The braiding coefficient, right? Here's attached here to the 1/3 and 2/3 braids. And here, those braids are on our terminal boundary. Planck length, Planck mass over the Planck charge squared. Remember, that's always the terminal boundary. All right, and now we look at the predictions. So with this equation, the alpha Feigenbaum constant is a constant of math. All of these numbers are things that you can easily look up and type into Wolfram Alpha or any calculating system you want, right? And solve. Now that we've calculated our mass of our electron before, you can put that in the equation and solve for mass of the proton. And then you can put that into the second equation and solve for the mass of the neutron. And what do you get? You get precise, exact, perfect predictions in both cases. All right. Now, remember, this is the orthogonal extension under our symmetry conditions of the elemental or trivial tessellation of the Planck mass boundary, okay? The mass boundary. There's only one mass boundary, all right? The Planck mass boundary has been twisted specifically, exactly, and most elegantly into the electron. But if you look at it orthogonally in two different ways, that electron looks like a proton or a neutron. Wow, that's really beautiful insight. This splitting and joining map, maintaining this balance, is setting up a really nice symmetry. But to get from here to all the rest of the masses, now, first of all, let's celebrate. We've already predicted the three most important ones to every significant digit perfectly. We've already seen the construction that's geometrically making the balance that we are calling mass, right? So we've gotten a geometric, visceral understanding of the geometry that's defining this system. All right, well, let's continue. So because the hyperbolic figure eight knot externally fibers under two orthogonal circular actions. So what structure is made up of two circles? Well, in this case, it fibers so that the two circles trace the boundary of a once punctured torus. Okay, so we form a torus here. That boundary defines the orthogonal intersection of two squarely arranged circle splittings and one joining of circles. So we have two splittings in two orthogonal arranged directions, okay? These are our red pictures here in the figure. We're splitting two circles in two orthogonal ways, but in the third orthogonal way, we're joining two circles. We're maintaining the joining of that, right? All right, well, here we go. Now, remember, back up a little bit, we've got the description of our mass boundary, just from our Planck mass boundary, just from the division balance of the hyperbolic figure eight knot. Then we say, okay, well, the geometric arrangement of that boundary must be in the form of the mass of the electron, which happens to be exactly wrapped by the hyperbolic figure eight knot, right? So now we've got the elemental tessellation of the mass boundary. We've got the extended splitting map and joining map of the elemental boundary. Now we just have to extend those maps to mirror the internal structure of our balance. So mirroring the internal division structure of the hyperbolic figure eight knots complement volume, which we got a cross-section picture here, okay? Which is composed of 6 circles surrounding a central circle that successfully undergoes 4 orthogonally arranged bifurcations. Okay, so look on the right side of the picture here. We've got 6 of these things that are arranged. Go inside, now you've got 1. Go inside, you've got a split, and then you can squarely split 3 more ways, okay? So this structure is now going to be mirrored externally, and that mirroring, that structure alone, extends what we've already seen perfectly to give us all the rest of the fundamental particles of matter, to predict every single particle of matter. So let's start this again. Mirroring the internal division structure of the hyperbolic figure eight knots complement volume, which is composed of 6 circles surrounding a central circle that successively undergoes 4 orthogonally arranged bifurcations, just like we see here. The joining map of the 3 trivial tessellations, the mass of the electron, the proton, and the neutron, extends into a balance of externally phased and internally folded tessellations. And the orthogonally connected splitting map, right, it's connected the whole time, extends into a balance of twists, splits, and flips. These extensions both simultaneously capture all 17 mass tilings. Here we go, the full joining map. Now this is the explanation for why these particles have the masses they have, because they are under this balance. These are the possible expressions, the orthogonal possible expressions of the complex motions going on the mass boundary, but they all tessellate the same mass boundary, the same arrangement on the mass boundary under different tessellations. This is the arrangement. This is the tessellation arrangement structure, our full joining map, right? Notice above we have the external phases, and then we have below the internal folds. And in the external phase regime, there's three possible phases: -1, 0, and +1. We've seen that before, right? Below, though, it's not different, it's three different phases. Those three things then have to be folded. So we get a fold and an extra fold and an extra fold as we go down, colored in red. Above, we also have a splitting or a squaring on that 1/3. Okay, so we have one upset there and one upset below, with a doubling on the mass of the strange particle, the strange quark. Okay, then let's just look at the left sides, right? Now we look at the right sides here, and we have, first of all of them in this joining map are pluses. Everything on the right side of the equal sign are all pluses, right? We're all adding things together. On the top, on the external phases, we can see that the one above and below have a symmetry. First, they're both connected by J2 squared over J1 cubed, so they both share that in common. But the down, up, and electron combination are connected through the Dotty constant, okay, which is the unique real root of the cosine function. So it's a universal attracting fixed point, okay, called the Dotty number. So when you have intersecting cosines, here we've got it to the cubed. In the upper expression, we use Gauss's constant to the -3rd power. So you see the combination here is geometric. We have the Dotty constant and the Gauss constant connecting. And then we have, well, the rest is pretty simple. The +2/3, notice, connects not from here, but to the next map, to the splitting map, right? To the -1/3 e to the 3 gamma, and so on. All right, notice below in the internal folds, still on the joining map, the internal folds section, notice we have on the right-hand side 2 of the terms that cancel to 0. Okay, really beautiful cancellation here. Let's continue now. The full splitting map. Okay, this is also orthogonally capturing the geometry, right? So the splitting map and the joining maps are both telling the same story from different sides, but that's why they're both able to capture these arrangements and then therefore express the values or predict and select the values of the masses. So here we've got the splitting map. Remember, it's alpha Feigenbaum -1 squared and the 2/3 squared thing, right? But here we have different versions of the splitting, right? Different expressions. We have the cubed power, the second power, and the first power. And with the cubed power, we're getting a squared bifurcation. With the second power, we're getting a squared hyperbolic bifurcation. But with the first power, there's no bifurcation happening. Okay, so we've gone down in scale where there's not room for splits. Cool. If we go down to the flip split balance on the inside here, we got the most unique thing to notice is that the central equation has 3 zeros. The 2/3, the alpha Feigenbaum -1, and the external action, the terminal action, have all canceled. This is the central crossing here of this action. And what does it represent, or what does it single out? The Euler-Mascheroni constant, that braiding constant. Okay? Now notice what it's in association with. Above and below, we have a negative square root, and above and below, we have a split and a flip. So e to the pi I is -1, it's a flip. Negative e to the 2 gamma is a splitting, it's a 2 braids, so you got 2 streamers coming off of that, okay? So we have a splitting and we have a flipping. So these are 2 geometric balances, but in order to make those balances in the middle, everything twists around, so all the other terms cancel. really beautiful. But this means that our math has to be extremely precise, because the second term has no correction factor out there. Everything has to go to at least, 14 significant digits. Meaning we have to have values for the mass of the up, strange, and down quarks that combine, according to this equation, to give us the Euler-Mascheroni constant. Really, really beautiful. Let's see how this works. Let's continue on down, and now we're going to focus on going on the individual tessellations. So chapter 9, okay? Every unique tessellation of this mass boundary represents a fundamental geometric tiling from which the hyperbolic figure-8 knots external mass boundary can be periodically constructed. These tilings are either geometrically combinatorial, so they're composed of an inverted balance stabilized between two actions, the second of which is always on the termination boundary, or they're primitive, referencing a single geometric action. Let's examine the geometry of each tiling, okay? This is something that's really going to blow your mind. The charm quark, right off the bat, we're going to have everything in comparison to the electron, because it's the elemental tiling, okay? So the electron compared to the charm, times by the J2 over J1 squared, equals the Dotty number. That's it, equals the Dotty number out to every significant digit, okay? The down quark, the mass of the electron over the down quark equals mu, remember a non-trivial zero, the logarithmic integral, divided by J2 squared, the second solution of our hyperbolic vortex equation squared. Also, again, look at the digits. Of course, the charm quark and the down quark, we didn't really know really well, right? We had a few significant digits there. So up quark, the mass of the electron over the mass of the up quark, equals 2 over the omega 2 constant to the nth power, to the 5th power. Okay, the omega 2 constant, remember, you might remember from a few chapters back, was one of those lemniscatic expressions, right? One of those balances in our lemniscate. It's equal to gamma cubed of 1/3 over 4 pi. All right, now we have this number out to all those digits. Great. The strange quark mass, let me pause and we'll go from there to go up and say, all right, and we'll go back up to our combination equations here. And we notice that in the flip-split balance domain, the up, strange, and down combine perfectly to every significant digit out there, right? All the way out to our 14, perfectly give us the Euler-Mascheroni constant. Perfectly. Those three geometric balances combine to define that braid. Beautiful. Okay, look at them again. It was the up, strange, and down. Here we go. Okay, the bottom quark mass. And we can kind of move through these fast now, because it's every person needs to spend some time really absorbing to see what's going on, let it click in. But I want you to get a feel for what's happening. We're comparing the mass of the electron to any other mass, okay? And it's always got some sort of geometric, simple expression. It's a simple geometric expression, but also of the form that is identified by our hyperbolic figure-8 knot, right? The geometric actions that are of our balance. Beautiful. So we're defining specifically each action. Here we've got the first lemniscate constant playing a role. In the top quark, we've got the second lemniscate constant. In the Higgs, we have, what is this? The first root of the Bessel function. In the Z boson, we got the Laplace limit. 1 over the Laplace limit is equal to the hyperbolic sine of the real fixed point of the hyperbolic cotangent. Okay, so there's a limiting action there. When you get a balance, you form the hyperbolic cotangent, you go around a point. The limiting swath action when you're forming this Laplacian shape, okay, is defined literally by this hyperbolic cotangent point. So, fantastic. The W boson, this is one that's really, really beautiful. As you probably know, the zeta function is world famous, and the zeros, the non-trivial zeros of the zeta function, explaining how they come to be where they are, explaining that sequence, is considered the treasure of all mathematics. Here we found that the reality divides in a way such that when it comes to the W boson's mass, its mass is set in a way that depends on the value of the first non-trivial root of the zeta function, the imaginary value of the first non-trivial root of the zeta function, which means the structure of the zeta function, which you probably would guess since you know that the gamma function is structured on the charge boundary, right? Is structured into this action from the charge boundary, and the zeta function is related to derivatives of the gamma function. But here we've identified, the Dottie constant for one of them. Another one identifies the actual first position of the non-trivial zeros in that function. Beautiful. Okay, we've got tau mass and the muon mass. These are all worth going through and really pouring over the details, but the point is that now we have a list of parameters that describe our geometry, the partition parameters of the hyperbolic figure-8 knot. We know n is 5, b is 7. We know there's these 5 external rotations, what their values are. And note, I don't know if I mentioned this before, but note that they are periodic in I. So 2 pi I times whatever whole number k, okay? We've got the Planck time, Planck length, Planck charge, Planck mass, and Planck temperature perfectly defined now as the boundary conditions of this balance. And we've got a bunch of geometric numbers that characterize specific parts of this balance, right? The volume of the hyperbolic figure-8 knot, Euler's number, Archimedes constant, or pi. We've got these 4 hyperbolic vortex solutions. We've got the alpha Feigenbaum constant, the delta Feigenbaum constant, which we haven't brought in yet, the Euler-Mascheroni constant, the non-trivial zero, the logarithmic integral. These are all the most elemental and powerful geometric constants there are, right? Gauss's constant, the lemniscate constants, the Dottie number, the omega-1 constant, omega-2 constant, the universal parabolic constant, the Kitchener harmonic mean, the first root of the Bessel function, the Laplace limit, which is connected to the real fixed point of the hyperbolic cotangent, and the first non-trivial zero of the zeta function. And now all of these mass assignments are also specific partition values defined by the hyperbolic figure-8 knot, by the boundary that we call the mass boundary in that balance, right? These are all its possible specific partitions or tileings. Great. So we have all these constants now that specifically explain the geometric aspects of our balance. But we're not done, because now that we've gotten our tileings of charge, or our connection between charge and mass, and we've partitioned them, we now need to define the balanced intersections that are maintained throughout this entire structure. Every unique balanced intersection maintained. Chapter 10, the constants of nature. So far, we found that the balance of the hyperbolic figure-8 knot is responsible for the persistent arena of reality, minimally decomposing into 5 unique actions, time, space, charge, mass, and temperature, with sharply defined boundaries, the Planck constants. The 2 external expressions of that balance, its charge and mass boundaries, connect via the hyperbolic vortex equation. And the 17 possible tessellations of that connection define the charge and mass values of all the fundamental particles of matter. In this chapter, we identify the remaining actions of this partition balance, revealing the geometry that defines the balance of each unique boundary intersection within the hyperbolic figure-8 knot. We discover that every unique partition balance defines a constant of nature. Therefore, every constant of nature is uniquely defined in terms of the hyperbolic figure-8 knot's partition constants, and uniquely defines one of the balances of those elementary partitions. So we've got a balance template here, so that if you want to spend time really looking into the constants of nature and what geometry they are referring to, what action, what balance, and so on, what boundaries are involved, this balance template should help. First of all, the symbol on the left will be the constant of nature that you're talking about, right? But it'll always be broken into a primary boundary and a terminal boundary action, if there's 2 of them involved. It could be just the primary one. And there's going to be some geometric primary action. In this case, when we have the competent wavelength as our template, okay, then the primary action is just 2 pi. It's pretty easy to interpret geometrically. The boundary of that action is playing on is the Planck length times by the Planck mass over the mass of the electron. Okay, so that intersection. Now, the terminal boundary, of course, is always the Planck length times the Planck mass divided by the Planck charge squared. it has a terminal action, another geometric expression out in front of it. In this case, it happens to be the alpha-Fuggerman constant, our splitting coefficient, times by b over 2, 7 over 2, right? That's our break and scale symmetry split. Okay, great. Also a beautiful equation. All right, well, when we go through here, notice the fine structure constant, the number that Dirac perfectly pointed out. We're not going to make any progress in physics until we understand this number. This number geometrically defines a squarely intersected hyperbolic vortex, right? That's the arrangement we have. If you take the first solution of the hyperbolic vortex, square it, you get the fine structure constant. Continuing, if we take the Planck charge and times it, like we've gone through this one before, and multiply it by the first solution of the hyperbolic vortex equation, you get the elementary charge, the charge of the electron, and look how accurate. The Compton wavelength we've mentioned, look how accurate. The Josephine constant. In every case here, we have an action, a geometric action balanced against another geometric action on a certain intersection of boundaries. And every intersection of boundary is just one of the parameters we've already listed, right? Either a Planck constant or one of the partitions of mass that are available in this arrangement. The balance defines the actions under play. The actions are also inversely under play. Look at this too, the electric constant and Coulomb's constant. First of all, on the primary action, on electric constant, it's Planck time squared, Planck charge squared over Planck length cubed and the Planck mass. The Coulomb constant's primary action has exactly inverted boundaries, just one over each other, right? Planck length cubed on top, Planck mass on top, right? Planck time squared on bottom, Planck charge squared on bottom. Okay, so that's just inverted. The only difference is the geometric action of the Coulomb constant is just 1, and the geometric action of the electric constant is 1 over 4 pi. Now look at the right side. On the right side, we have a 1 minus in the electric constant and a 1 plus in the Coulomb's constant of the same thing. N squared over 2 to the n, of a boundary squaring over the boundary doubling, or doubling to the fifth power. So that's a 32. All right. So this inversion is really, really, really beautiful. We have a circle, we have a unit to a circle, but then we have an inversion here. So when we invert the boundaries on the left, we invert the boundaries under an orientation on the right. Beautiful. Okay, we can go through all these equations. What I really want you to note is that in every case where we have a constant measured to lots of significant digits, or even when we only know a little bit, we always get it right. This simple expression, just picked by the units here, okay, you can, in fact, it's really easy to figure out how to solve these problems. You can just go to the units of the number. This one's meters cubed kilograms over seconds squared Coulomb squared. So you're going to say, well, meters cubed. I'm going to take the Planck length cubed. That's because that's our only natural boundary in meters, right, in length. And then kilograms, well, our kilogram boundary is our Planck mass boundary. So, and then divided by seconds squared. Well, our time boundary is the Planck time boundary. Then our charge boundary is the Planck charge boundary. So in each case, you look at the dimensional units, and it tells you the construction of the primary boundary. Right? The terminal boundary is always fixed. So the primary boundary is just determined by the dimensional units of your number. Awesome. Okay, so I'm going to scroll through these so you can go through. I really want you to pay attention to how simple and elegant they are. Right? Look at this. There's a limit state constant under hyperbolic balance with the hyperbolic vortex solution, second one squared. So beautiful. We have another return of the imaginary part of the first non-trivial root of the zeta function here in the Bohr electron radius and in the atomic mass constant. So there's a lot more to the story here, but I think it's a good start for everyone to maybe get their head wrapped around this construction, right? Let me scroll down. It's so beautiful. All the geometry in this is really, really beautiful. Get your head wrapped around the construction so that you can see what the geometry is saying. But also, the really important thing to keep in mind is that all of this is just one geometric structure with many balanced parts. Every unique balance in this structure defines a unique action of reality, a constant of nature or a partition of mass. All of them come from this one single balance. Okay. So now that we've defined all the constants of nature, we're in possession of a complete partition balance of the hyperbolic figure-8 knot, the constructive legend of physical reality. We've got the whole legend in hand now. We've got finally the rule set for the chess game, for reality. And now it's time to learn how to play. Here, we've got a complete partition parameters, complete set of the partition parameters of the hyperbolic figure-8 knot. Okay, so you scroll through, we've got an updated set now. All the numbers you've seen before are geometric numbers of our geometry, our mass partitions, our constants of nature, and what their values are. Okay, remember the green digits are the new, those are the ones were predicted even further. Every green digit is another prediction of this model. Every black digit that precedes it is another digit it got right. There are none it gets wrong. All right, at the end here, we have a section of constants also included in the constants of nature list that I haven't said anything about at all. The Franz-Robbins constant, right, all the way down to the power tower of I. These are all important structurally, but I think I'm going to leave it at this because that discussion becomes, well, honestly, because I haven't finished wrapping up that discussion. I'm still exploring it myself. But this was certainly enough to get everyone going. We've got a simple geometry that clearly makes more predictions than any other model in the history of predictions. Here, 1,100 digits predicted. There's 436 digits total in all of the parameters of quantum field theory that need to be explained, based on our best accurate measurements. Collectively, 436, if I got them all right and counted them up right. But either way, it's roughly close. And here, we've got them all, and then continued to predict. We could have extended it, of course, but I think really at 14 is where we cut off. Or I think I cut it off at 15 here. So we've got 1,100 digits. We've made more we've verified everything in quantum field theory in one simple model and predicted its precision more than double. Fantastic, beautiful. I really love the precision that comes with this. All right, now we close out chapter 11. Notice. For nearly a century, physicists have been warned against trying to understand physics. The standard mantra, as has been repeated over and over, is shut up and calculate. That is, simply do not think about how to understand the world. Just grind out predictions. And not being trained or encouraged, indeed being actively discouraged from trying to think clearly about that question, leaves most physicists in no position to make well-considered comments about it. Tim Maudlin. We lost academic freedom, and then we ushered in peer review, which was a disaster, and then we lost funding. Eric Weinstein. A common response I hear is, I can't wait to hear what other physicists have to say about this. Somehow people are blissfully unaware of the situation we are in. There are no people professionally in this conversation. Period. No physicists, no philosophers or mathematicians in the entire world are currently getting paid, including me, to work on this topic. Not a penny. This conversation is up to us to resurrect. When the average person thinks of physics, they seem to think of it as it was in the time of Einstein, when researchers could still professionally pursue questions of their own choosing. Today, things are different. Under the modern peer review system, those controlling the research money control the conversation of humanity, deciding what gets explored and, more importantly, what doesn't. And as every physics graduate student discovers, with shock, those in charge have deemed the theory of everything as an unfundable topic, the modern way of saying forbidden conversation. In today's world, if you want to get paid, then you must pick a different topic. And with that sleight of hand, the most honest questions we can ask are no longer allowed. The modern focus has backfired on us all, effectively snuffing out the most noble part of existence, honest exploration of one's reality. I believe we have just outlined the most accurate understanding of reality structure that has ever existed, and that this elegant perspective is capable of initiating the next great awakening of humanity. But seeing how this is happening at a point in history in which the battle has already been lost, in which there's nobody left in the conversation, the first step is to make this a world in which this conversation is, once again, safe. To date, despite having been trained as a physicist and having worked at NASA, I have yet to meet another individual that I know has taken the first step in figuring out the biggest puzzle of all time. Compiling a list of the parameters that define the mysteries of quantum field theory. Literally everybody, no matter what their position or financial fortune, finds themselves in a world in which it is not safe to ask the most honest questions one can ask about the makeup of reality. If you'd like to live in a world that incentivizes its individuals to think about how to understand the world, please consider supporting this research. Chapter 12, coming up. One of the delightful surprises of this construction is that one of its partition parameters inversely depends on the square root of the imaginary part of the first non-trivial zero of the Riemann zeta function, while another depends on the square of that number, structurally balancing the first zero in the most famous sequence of zeros in all of math. Obviously, there's more to the story here, but I've been told that every math equation put into a book cuts its audience in half, so since by that logic it should take quite some time to find a reader all the way down here, I'll cut the story off here for now and get back to working on enhancing my own understanding. If you would like to join this effort to understand the world, I recommend getting the extended version of this book, titled 44, once you've absorbed this one, because I haven't published it yet, so give me some time. It will include several appendices of organized geometric relations, far more than we've included here. I tried to streamline and keep it short here, relaying secrets about reality's construction never seen before. I mean, obviously we've done that here too, but there's far more. This is the tip of the iceberg, honestly. There's so much more that follows out. I also recommend verifying everything. Okay, I recommend verifying everything in this book for yourself. Right? That's literally the point. It doesn't do anybody any good unless it's a comprehension you've obtained. I also recommend really getting to know the geometric equations in this book that define the balances of reality, the logic of persistence. All right, that's it for my guided reading of the new book, Source Code, Balance of Persistence. If you valued the content in this book or video, please consider supporting the continuation of this research. If you don't have the financial ability to support that way, maybe support by investing more time in to develop your understanding the geometric connections in this model. Also, we can look at the equations of the constants of nature, all side by side next to each other, to help better develop our intuition, our rich geometric, precise understanding of what each one is saying. All right, thanks for your time and your space and charge and mass and temperature.